On March 11, 2026, at 19 hours, 22 minutes and 54 seconds UTC, a 25-centimeter telescope in Italy captured 10 exposures of 120 seconds each, stacked them, and produced an image. It shows a faint, slightly fuzzy point of light against a field of stars. No tail visible, no coma structure, no jets, just a point, magnitude 16.4, drifting slowly against the background. That image, taken by astronomer Toni Scarmato and published by Loeb 3 days later, is the last known photograph of 3I Atlas before it passed Jupiter on March 16th and began its permanent exit from our solar system. 5 days after that photo was taken, 3I Atlas was gone. Not gone as in destroyed, gone as in past the point where it will ever come back, gone as in heading towards Saturn, then Uranus, then Neptune, then interstellar space, forever. The image itself is not dramatic. It does not show anything new. It does not resolve any of the 22 anomalies. It does not answer the mass budget question or close the sublimation paradox. What it shows is an object leaving, and I want to spend today with that image, not just what it reveals scientifically, though it does reveal something, but what it means to have watched something for 9 months, to have measured it with every telescope we had, to have documented 22 things we cannot explain, and then to watch it become a faint point drifting away until even that point disappears. Because I think that image deserves more than a data point. I think it deserves to be understood. Stay with me. The image itself, what you are looking at. Let me describe the photograph precisely, because the details matter. 10 exposures of 120 seconds each, that is 20 minutes of total integration time. The telescope aperture is 25 centimeters, roughly 10 inches. This is a serious amateur telescope, not a professional facility. The angular resolution is 1.38 arcseconds per pixel. At the distance, 3I Atlas was on March 11th, approximately 3.9 astronomical units from the Sun, roughly 3.2 AU from Earth. 1 arcsecond corresponds to roughly 2,300 kilometers on the sky. So each pixel in this image covers an area about 3,200 kilometers across. The nucleus of 3I Atlas is 2.6 kilometers in diameter. It is completely unresolved. It is far smaller than 1 pixel. What you see in the image is not the nucleus. It is the integrated light of the nucleus plus whatever residual coma still surrounds it, smeared across a point spread function determined by the atmosphere and the optics. The fact that it is visible at all is remarkable. At magnitude 16.4, 3I Atlas is approximately 40,000 times fainter than the dimmest star you can see with the naked eye on a clear night. Detecting it requires stacking multiple exposures, precise tracking to follow the comet's motion against the background stars, and careful image processing to pull the signal out of the noise. Toni Scarmato has been imaging 3I Atlas since its discovery. He is one of the independent Italian astronomers who collaborated with Loeb on the Larsen-Secchionina filter analysis of the Hubble images, the analysis that revealed the 3 mini-jets at 120 degrees separation. He has been watching this object for 9 months. When he took this image on March 11th, he knew it was probably the last one he would ever take of 3I Atlas. The comet was 5 days from Jupiter. After the flyby, it would accelerate outward and fade below the reach of his instrument within weeks. He took the image anyway. 10 exposures of 120 seconds, because that is what you do when something is leaving and you want to record that it was there. What the fading tells us scientifically. The brightness of 3I Atlas on March 11th, magnitude 16.4, is itself a data point, and it is an interesting one. At 3.9 AU from the Sun, the solar flux is about 6.5% of what it is at Earth's distance. At this level of solar heating, Water ice sublimation has essentially stopped. The sublimation temperature of water requires more solar energy than is available at this distance. CO2 sublimation, which requires less energy, may still be occurring weakly. CO sublimation can persist even further out. The brightness at this distance reflects two components: reflected sunlight from the nucleus surface and any residual coma from continuing low-level outgassing. The fact that 3I Atlas is still visible and still slightly fuzzy, still showing a hint of extended emission rather than a pure stellar point, suggests that some residual coma activity persists even at 3.9 AU. This is consistent with what we know about 3I Atlas's chemistry. CO was detected as a dominant volatile after perihelion, taking over from CO2 as the surface CO2 was depleted. CO sublimates at approximately 25 Kelvin, a temperature reached in the outer solar system well beyond Jupiter. If 3I Atlas retains a significant CO reservoir, it may remain weakly active for years after the Jupiter flyby. The fading rate from the last few weeks of observation, how quickly the magnitude dropped from 16.4 toward the detection limit, constrains the outgassing rate at large distances. These measurements, combined with models of CO sublimation at low temperatures, give a constraint on how much CO is left in the nucleus. That number feeds into the mass budget. The total volatile inventory of 3I Atlas, water, CO2, CO, methanol, methane, was enormous at discovery. The solar passage depleted some fraction. How much remains determines how long 3I Atlas will continue to be active as it recedes into the outer solar system and eventually into interstellar space. The last photo, and the fading curve it sits on, is not just a sentimental record. It is a measurement. It will appear in papers. It will be used to constrain models. The 9 months, a timeline of discovery. Let me walk through what happened between July 1st, 2025 and March 11th, 2026. Not as a list of facts, we have done that, but as a narrative, because the pace of discovery was itself remarkable. July 1st, 2025. Atlas Chile detects a moving point. Within 6 hours, the Zwicky Transient Facility finds pre-discovery images going back to June 14th. Within 24 hours, the orbit is computed. Eccentricity, 6.15. The number that changes everything. An eccentricity above 1 means hyperbolic, means interstellar, means not from here. The Minor Planet Center assigns the designation 3I Atlas on July 2nd. July through August, the telescopes mobilize. Hubble images the nucleus on July 21st. Swift detects hydroxyl, water, on July 31st. 40 kilograms per second of water at 2.5 AU from the Sun. Webb NIRSpec observes on August 6th, CO2 dominant coma, CO2 to water ratio of 7.6, 4.5 sigma above the trend for all known comets. ALMA detects methanol on August 28th, 8% of total vapor, 4 times the solar system average. September through October, the approach to perihelion, Mars flyby on October 3rd, 29 million kilometers. Parker Solar Probe observations from October 18th through November 5th. Perihelion on October 29th at 1:36 AU. Earth on the opposite side of the Sun. The most active phase of the entire passage, invisible from Earth. November through December, reemergence. The comet reappears from solar conjunction on November the 1st. Meerkat detects hydroxyl at radio wavelengths on October 24th, 5 days before perihelion, the first radio detection of an interstellar comet ever. JUICE observes with 5 instruments from November 2nd to 25th. SphereX reobserves in December, water 20 times brighter than before, organics in the coma, methanol, formaldehyde, methane, ethane. December 19th, closest approach to Earth, 180 AU, 270 million kilometers. The furthest closest approach of any interstellar object we have tracked. January 2026. The opposition alignment on January 22nd, Sun, Earth, and 3I Atlas within 0.69 degrees. Hubble captures 40 post-perihelion images. The Larsen-Sekanina filter reveals 3 mini-jets at exactly 120 degrees separation. TESS produces a 28-hour time-lapse. The rotation period, 7.1 hours, more than doubled since discovery. February through early March. The fading begins. The object recedes. Observations become harder. The papers accumulate. The mass budget, the isotopes, the ALMA formal publication, Loeb's 22 anomalies. March 11th, the last photograph. Magnitude 16.4, a faint point in Gemini. March 16th, Jupiter flyby, gone. 9 months from a moving dot in a Chilean telescope to a published body of scientific literature that will be analyzed for years. What we learned, the permanent results. Some of what 3I Atlas taught us will be debated for years. The anomalies, the mass contradiction, the energy budget, the 120-degree jets. But some results are permanent. They will not be overturned. They are in the literature, confirmed by multiple instruments, independently reproduced. Let me name them. First, interstellar comets carry prebiotic chemistry at concentrations that exceed solar system averages. The methanol at 8%, the HCN, the formaldehyde, these are not trace amounts. They are dominant components of the volatile inventory. The first confirmed interstellar comet, Borisov, had chemistry similar to solar system comets. 3I Atlas is different. The chemistry of interstellar objects is not uniform. It reflects the diversity of stellar environments. Second, the DH ratio in interstellar water is not the same as in solar system water. 3I Atlas's water is 10 times more deuterium enriched than any solar system comet. This is a permanent measurement. It means that water chemistry varies across the galaxy in ways that are directly measurable, not just inferred from stellar spectra or theoretical models, but measured in the gas released by a physical object that passed through our solar system. Third, interstellar objects can be much larger than our detection methods previously implied. The initial estimates for 3I Atlas ranged from 440 meters to 5.6 kilometers. The Hubble post-perihelion measurement settled on 2.6 kilometers. That is large, 40 times more massive than Borisov, orders of magnitude more massive than Oumuamua. If 3I Atlas is representative, the interstellar object population includes bodies large enough to carry significant chemical payloads and to remain active for extended periods during solar passages. Fourth, the basic physics of cometary activity is universal. The hydroxyl transition detected by Meerkat in 3I Atlas, the flip from absorption to emission as solar UV pumping shifts the OH maser state, is the same physics observed in dozens of solar system comets. It does not care which star the comet formed around. Water photodissociates the same way. O radiates at the same frequencies. The fundamental chemistry of comets is not parochial. It is a property of molecular physics, which does not vary across the galaxy. These 4 results are solid. They will be cited. They will inform the interpretation of every interstellar object detected after 3I Atlas. What we didn't learn, the open questions. And then there is what we did not learn. The questions that 3I Atlas leaves open, not because the instruments failed, but because the measurements were taken from too far away, or because the physics is genuinely unresolved, or because the object left before we could finish asking. We did not learn what the interior looks like. The December 2025 eruption gave us a glimpse of subsurface chemistry, the methane, the organics buried under a 10-meter crust. But the depth profile, the thermal structure, the boundary between the radiation-processed exterior and the pristine interior, unknown. A spacecraft at 1,000 kilometers could have mapped this. We did not send one. We did not resolve the mass contradiction. The sublimation rate implies a nucleus larger than 3 kilometers. The non-gravitational acceleration implies a nucleus smaller than 2.3 kilometers. These two measurements cannot both be correct under standard physical assumptions. The post-flyby astrometric data may tighten the constraint, but the fundamental tension between the two methods is not resolved. We did not explain the 120-degree jets. 3 jets, equally spaced, consistently present across 40 Hubble images over 4 months. No natural model produces this geometry reliably. The permafrost hypothesis invokes structural features of the nucleus, cracks at specific angles, but cannot predict those cracks from first principles. The alternative hypothesis, technological thrusters, is not excluded by any measurement we made, but is also not supported by any measurement we made. We did not identify the parent stellar system. The isotope measurements narrow the birth environment to old, low metallicity, cold, 10 to 12 billion years ago, below 30 Kelvin metal-poor galactic disk, but we cannot trace the trajectory back 10 billion years through a galaxy that has rotated multiple times since then. The specific star that ejected 3I Atlas is unknown and unknowable. We did not understand the nickel. The Ni-Fe ratio started at 3.2, far above anything in solar system comets, comparable to industrial alloys, and declined to solar system values as the surface was depleted. This is consistent with a surface layer that had an anomalous composition, possibly accumulated during interstellar travel, possibly reflecting the original formation environment. Both explanations are possible. Neither is confirmed. These open questions are not failures. They are the residue of genuine contact with something genuinely unknown. We touched it. We measured it. We could not fully read it. Where it is now. Let me tell you where 3I Atlas is today, March 26, 2026, 10 days after the Jupiter flyby. It is approximately 4.2 astronomical units from the Sun, between the orbits of Jupiter and Saturn. It is moving at roughly 58 kilometers per second relative to the Sun. It is in the constellation Gemini, continuing to drift northeast, but now below the detection threshold of any telescope smaller than 8 meters. The Vera C. Rubin Observatory, now fully operational, is technically capable of detecting it for perhaps a few more weeks. After that, only the very largest ground-based telescopes will see it, and only with extreme integration times. By mid-2026, it will be beyond Saturn's orbit. By April 2027, beyond Uranus. By 2028, beyond Neptune. Sometime in the early 2030s, it will cross the heliopause, the boundary where the solar wind gives way to interstellar space, and re-enter the environment it came from. It will then travel for billions of years. The slight changes the solar passage made to its surface, the depleted volatiles, the altered dust layer, the new cracks from the December eruption, will persist. The 15 million metric tons of material it shed in our solar system will disperse and eventually be absorbed into the solar system's inventory of interplanetary dust and planetary surfaces. And the other 985 million metric tons, the pristine interior, the 10 billion-year-old prebiotic chemistry, the deuterium-enriched water ice, will continue its journey to wherever it is going. We do not know where that is. We cannot track it. We can only know the direction it came from and the direction it is heading, toward the constellations of the outer Milky Way. It will not stop. It has no destination that we know of. It will drift until it passes close enough to another star to be pulled in by gravity, in millions or billions of years, or until the Milky Way itself changes beyond recognition. The last photograph of 3I Atlas is a faint point of light in a field of stars, 10 exposures of 120 seconds each, a 25-centimeter telescope in Italy, March 11, 2026. It does not show the nucleus. It does not show the jets. It does not show the anomalies or the deuterium or the missing iron or the 120-degree symmetry. It shows a point, but that point traveled for 10 to 12 billion years to be there. It formed in the early Milky Way in a stellar system we will never identify, from a molecular cloud that no longer exists. It drifted through interstellar space while our galaxy formed its spiral arms, while our sun ignited from a collapsing gas cloud, while Earth formed and cooled and filled with oceans and life. And then, for 9 months, it was here. We measured it. We argued about it. We published 22 anomalies and a mass contradiction and a DH ratio that breaks the solar system average by a factor of 10. We pointed every telescope we had at it and filled journals with what we found. And then it left, and Toni Scarmato pointed a 25-centimeter telescope at it one last time, stacked 10 frames of 120 seconds, and recorded that it was still there. Magnitude 16.4, faint, drifting. That image is the last record of physical contact between our civilization and a messenger from the early universe. I think that deserves to be said out loud. Subscribe to follow what comes next. The post-flyby science, the JUICE team meeting results, and the next interstellar object that Rubin Observatory will find, probably within the next few years. When it arrives, we will be here. And if this video meant something to you, if you spent the last 9 months following this object and you feel something watching it go, leave a comment. Tell me what it meant to you. Because science is not just measurement, it is also the experience of standing at the edge of what we know and watching something pass by that we cannot fully explain. 3i Atlas gave us both.